Is it fine?
Yeah, looks good. It's full screen. Perfect. Thanks.
Thank you. So I will start my talk on human robot synchronization for musical ensemble. So here is me and Joe. We were working in 2019 Dublin's Maker Fair, and we took the photo over there. So we showed some demo over there, and after COVID, everything stopped, and it was very sad. But hopefully next year we find something new. So Joe is my supervisor. He's also the head of the department in computer science at Mendip University. And the main question of our research is, can robots play music with humans and like humans? So basically, when we see robots, they just respond to humans. They doesn't interact with us the way other human does with one each other. So our question is, can this bond be created between robots and human, so that the synchronization or the coordination between them is very free and like human like. So in this presentation, we will go through a detailed survey about each and every present technologies and how synchronization happens, and then we discuss about the designing the you know the model which we are trying to create for this particular, for achieving this particular uh, project. And then we have some issues with selecting the leaders. We will come to that later. And then understanding beats from visual cues, so we'll discuss them, all of them, later. So these are the main 4 points on which we will be discussing today. So starting with the detailed survey, we had 4 questions in our mind. So the first question was, how are robots synchronized with human performance? This is a big question, how they are going to do. The second question is, what is the underlying factors that have that happens during the musical synchronization, like when two or more, or a large ensemble, or more than 10 people are playing together, the gestural movements, the musical movement, the musical features all interact with each other, and they come up with the final performance. So understanding all this kind of structure, the physics behind it. So we studied many of the papers, and we came out with some uh, advantage and disadvantage. We will be discussing about them in the next few slides. And then we have the third question, where we studied that how synchronization exactly works for a particular music ensemble. It's very domain specific question. And the last, the fourth question we had was the Kuramoto's model. It is an interesting phase synchronization model, and how it can be implemented to solve this kind of a problem. So let's start with the first question. We had few bots which are already present, and the research is going on. So we have the Shimon, introduced by the Georgia Tech group. We have the Mahadev bot, which is a drummer. And then we have the now robots, which is playing a theremin. So these are the robots which are already available, who tries to synchronize with human. But the main problem is they doesn't understand, or they doesn't predict the movements or the non-gestural motions. They just react to the music they are hearing. That's a big problem, because when human play music with each other, they try to understand what others are doing and what others are trying to do. So this kind of thing is absent in the traditional robots which are already there and playing with humans. So the next question was, what were the underlying features for human factors for human beings to understand synchronization? The four things is the sense of time. We know, when it's at dinner time, we feel hungry. If you listen to a small section of a song, you can predict the beats. So the sense of time is very important, which is an important factor which human has within themselves, but the robots doesn't have. Then we have a short memory. Just for example, if in the class during the dictation, we listen to the teacher, we listen to it and store it in our memories RAM, we can say it RAM. So we just store it inside our brain for a short time. We don't remember forever, just we listen and then we write. So this short memory helps us to get the data very fast and process it very fast and predict what is going to happen next. So if I say twinkle twinkle, automatically your mind says that the next word should be little star. So this is how the short memory works very fast. Next, we have the power to understand patterns and predict future. As I said, that we creating for creating music or interacting with people, we need to understand their pattern and predict the future. That's the important thing that machines can't do. So, for example, if you listen a song many times and then we can predict the forecast, the beats which we'll be following with the song, just after few minutes. So that is an important factor which humans have but machine doesn't have. And the fourth thing was the interesting thing, the ability to talk and speak. So we I discussed about this kakatu, which is bird. And Patel in his study, he discussed about how he tried to train a chimpanzee, monkeys, to predict beat and dance with songs, but they were unable to understand. But interestingly, the this kind of bird who knows how to talk was able to understand rhythm, was able to understand the pattern, the change in tempo. So what he did was he played the song "We Will Rock You," and the bird started to nod its head with the song. Then he tried to drastically change the tempo of the songs, just to make sure that whether the bird is not pre-trained with that song. So but to surprise, it was very successful in recognizing the change in the tempo. So basically, this is an important and interesting factor which helps this kind of features to understand the rhythm. So the basic difference with this bird with other birds is that it can talk, it can mimic the human voice. So it's a great ability, and the researchers found that that is the sense needed for understanding rhythms and interacting with other. So to understand a musical ensemble, we can consider it to be a connected graph where we have maybe 10 or more than 10 musicians. They are connected to each other and they are dependent on each other. For example, they are not only listening to their own sound. So the last point, if you see over here, I say that they can imagine their own sound. While the drummer is playing his drum, he can imagine how the drum will sound and what he's going to play. But also he's trying to listen the other people, the singer and everyone, so that he can maintain the beat and also interact with the other fellow musicians during the performance. Another interesting factor in this kind of ensemble scenario is that time varying leader and follower relationship. So for example, if you start some for traditional music, it starts with some kind of accompany instruments like piano, guitar, and then the drums comes in, bass comes in, and then there are some arpeggio in the middle. So every instrumentalist have their own time for playing, and they take the lead of the dominant factor. So they lead the whole performance at that time, and all the rhythm and all the timings depend upon their performance. If they they stop playing it, it's a mess. So the time varying leader and follower relationship is very important and plays a key role in this kind of musical ensemble. So the fourth question was answered, that what is Kuramoto's model. So Kuramoto's model is basically a synchronized phase synchronization model, mathematical model, where which we can implement in our case. So what we do is we consider each and every musician as an independent oscillator. So the musician, for example, we have two musicians, they kind of oscillate in different frequencies of their own. And if we can tie them in with the same rope, mathematical rope, then we see after some time they starts to flow, or they move, or they try to synchronize their movements, or they're playing beats, or in the same time. So that's the main concept by which we can use this kind of phase oscillators to solve this kind of synchronization problem. So the problem in the previous bots or in the previous robots, where they use kind of beat tracking algorithms, which used to listen to the beat and play with that beat. And what happens is, if the beat changes, if the tempo changes, they are again in a mess. So they can't foresee the small changes in beats. And also, when you are doing something in real time, there are enormous kind of noise which can be possible. Suppose the robots are moving, they create some of the noise during the motion, so the body motion. So this kind of noises are very lethal for maintaining the synchronization, because for fraction of time it can be a big deal. So if we introduce this kind of oscillator motion, which will help us in the later stage, we will see some of the results. It helps us to overcome this kind of distortion, or this kind of errors which happens when we use the beat tracking algorithms. So again, we say that each musicians are considered as a different oscillators, and we use the Kuramoto's oscillator to tie each of one of them with a single rope, and try to match their frequency together, so that they can work together. So this is the whole concept of having the Kuramoto's oscillator into this domain. And so again, I will just revise about the findings from this research. So we had the robots musician who uses beat tracking algorithms, and then our brain performs much better synchronization on group performance rather than duo or trio. This is because the interaction is a lot more. There is a non-verbal communication going on between the musicians, and that vocal learning, or the ability to speak, plays in an important role in understanding rhythm. And there is the mathematical phase synchronization models that can be a good solution for this. Then the Kuramoto's equation can be used in robot musicians to solve this kind of problem. The present robots, they just follow humans, they don't make music with humans, what was our target or our aim to see. Then we saw also that the body movements, the non-verbal communications are very important to take count into, so to understand the beats and the phase. And latency, yeah, so this is the whole setup should be in proper time. So latency is a very important challenge. If you're dealing with millifractions of seconds, the whole synchronization is gone. So latency is a key issue in this kind of scenario, where you have enormous amount of data to process and get some output in real time. So this is the ensemble network, just a picture. And there is an interconnected network where each and everyone is connected, everyone is connected to each other. And then there is a time varying leader and follower relationship among the musicians. So the model which we are trying to design, so this was published in the paper, the journal in Nature. So we thought about coming up of a plan about how to solve this problem. And we segregated this whole problem into two things. One is the mapping, and there's the modeling. I will discuss about it later. So we have the first stream of sensors. So we need some microphone sensors which will work as the ear of the robots. We have some MIDI protocol, or the MIDI keyboards or MIDI instruments to get the inputs very fast that what they're playing, in case we miss out some of the important musical signals due to noise. And then we have camera sensors to observe the gaze between which the musician is looking at, who is dominating the whole uh, ensemble at that particular point of time. And then there could be some wearable sensors or body motion sensors which will be useful for understanding the the body movement rhythm from the musicians, and then transferring that knowledge into some machine learning or deep learning model to get some feedback. And then we feed them into the Kuramoto's model for mapping all the timing of the beats, and this will help us to achieve the proper synchrony during the whole whole performance. So basically we divided the whole thing into a mapping and the modeling, where in the modeling they select the leader, they look at they try to predict the future, and in the mapping we just try to synchronize the phase directly and take some predictive feedback from the modeling you know part, and try to predict the phase. So again, so for synchronization and anticipation to work together, we have this mapping and modeling concept, so that it works together just like human does. So where we thought about how what we do when we play the music. So we not only play our thing, not only try to listen to the beats, but also try to observe the other players, their expressions, their body movements and body sway, to understand how how we should react with the music. So in kind of, when the piano player plays, sometimes he plays some of the notes very loudly, means the keystrokes are with more velocity, and some of the keys are very slow, and their emotion or their expression changes when they the kind of change their velocity or their body motion. So these are all related to each other, and this will play an important role for achieving synchronization and anticipation. So the next problem was the following the musical leader. So for this concept, what we thought is, let's consider a blind man who doesn't have any, who can't see. So if a blind man is listening to a particular ensemble, can he understand who is the leader? That was our goal. So in this work, what we created was a Lstm model whose name was leader stem, because we used the stem dataset. So the dataset had drums, the other comprises of the piano, the guitar, and other musical instruments, and then we had the bass and the vocals. So we tried to get the BPM or the tempo of each individual channels, and then our model was trying to predict who is the dominant character, or the musician who was dominating the output sequence. So if you go to the next slide, so you can see over here in the beginning, so the mixer track is the output track, and the sub track are the different instruments. So the mixer track says I was following the the BPM of the bass in the sorry the accompany in the beginning, and then I started following the drums, and then at the last I was following the bass again. So it was following the accompany, the drums, and the bass again. So the blue lines are the actual lines, which was the actual tempo, and the red lines are the individual instrument tempo. So we can see that it was following the accompany, the the bass, and then the drums. So this kind of models was successful. Means we trained this leader stem model, and it was kind of successful in understanding whom to consider as the real leader. But it was not, we can't say that it was very good in predicting, because the main thing was missing, that is the visuals. The visuals was missing. So a blind man can't see, and he can listen to the instruments, and he can predict that who is leading the show. But sometimes there are other factors as well, other musicians as well, who are leading the show. So it was kind of successful, but not fully. So on further investigation, on further research, we saw that the Kuramoto's model was very much efficient in trying to synchronize with that music, which was a single channel music. So the leader stem was able to understand the leader, and the Kuramoto oscillator was able to understand the face of the song. So you can see over here, we try to, we try to increase, we try to select a drum beat which was going, keep on, keeping on increasing after the time. And the oscillator was also, increasing its phase, means it was trying to match the phase with the song. But what happens is when the beat tracking algorithm stops to predict the, or for example, if the tempo is 120, the beat tracking algorithm again starts to predict it as a 60, because it's just the half value of the, double 120. So the bit tracking has a proper range. It's from 60 to 120. So anything beyond 120, it comes back to 60 again. So there is a drastical, change over here, we can see in the last part of the graph. But the Kuramoto's oscillator was not, it was not, all of a sudden it didn't came down. So that is the main important thing. We wanted it to be more stable than the normal beat tracking algorithms, so that, the robot doesn't fall into trap, and it doesn't give us, wrong outputs all of a sudden because of some, silly noise. So in the next example, we see the multiple source where, four musicians were playing. One was playing the flute, and another the oboe, and then clarinet and basson. And then we had this, the whole section where the oboe was leading the show, and then the flute joined, then the clarinet, and then the basson. So they used all these different instruments in different point of time, and you can see from the graph on the left hand side. And then we try to use this whole audio for Kuramoto synchronization again and again. It was very successful. And the main motive of this kind of piece was, we choose the art of fugue, and this particular piece had a change in tempo in various part of the, piece, and it was very successful in understanding all those kind of thing. So the result was very good, and we published the journal for that. So the last thing which I will be discussing was the visual cues. So it was like, let's see, when the musicians interact with each other, they try to see each other, and they try to predict the beat. So it's the other way around. We have a deaf person who can't listen to other people, but only can see. So we use kind of approach where we use firstly the motiongram, which was tracking the motion of, musicians, and it was trying to predict the motion of musicians, and we converted this motion into a different oscillators. And as you can see over here, their hands are moving, they're different, it depends upon, the instrument. So their hands are moving, and we are trying to generate a single motion variable from each and every musician, so that we can understand the audio beats, we can predict the audio beats from the from the video. So this was a very interesting challenge that we took. And we used two approaches for this. One was the motiongram, another was the pose estimation. And in pose estimation, we had two things. One was the considering the first frame to be the frame of reference, like whatever is the motion, we consider the first frame to be the first motion, and then whatever is the motion, it's just the difference between the first frame and the nth frame. And then we have the optical flow, where we calculated the differential, the difference between, the two consecutive frames, and try to build up emotion for each musicians. So from motiongram, we got this kind of graph, where we had the x, the y, and the z. So the x was the horizontal motions, the y was the vertical motions, and z was the quality of motion, like was it too much of motion, was it very less motion. So we tried to get this three data from the motiongram. And then what we did was we use some filtering methods to filter out the noise. And then we try to reduce the dimension of, we consider each signal to be three dimensions, so three axes, and then we reduce the dimension and then try to predict the beat using the peak detection technique, and I will show you the results. So after this, we had the pose estimation, where we try to understand the pose and try to predict the pose, and then try to predict the where the beat. The idea was simple. We considered each musician as a individual oscillators, just like the Kuramoto's thing, and we got this kind of motion from each musicians, and then we tried to predict like which of the motion means which are the beats from the musician motion. So that was very interesting to study. And when we studied more, we saw that the instruments played an important role. So in our data set, we had this kind of strings instrument, woodwind instruments, and the brass instruments, and we tried to cover all the instruments in one of the performances, and then we calculated the performance of 12 video files, and then without the audio, okay, and we are trying to guess the audio beats from this kind of video files. And when we tried to predict, we saw some interesting thing. That is, the motion gram was pretty consistent in understanding the motion from the visual cues, and means predicting the audio base from the visual cues. And then the open pose optical flow was again very consistent in understanding the motion from the predicting the beats, the audio beats from the visual cues. But the main thing which we found was that it depends upon the instrument. For example, if you have some instruments like the flute, the performance of motion gram was much better. Sorry, it was much bad, and the pose estimation was working very good because the human was moving while playing. But for other example, like violin, the musician was moving his hand too much, so the motion from that was very clear, that the motion from those hands was very clear for us to predict the audio beats. Uh, so we have a demo over here where we play a tap sound with the song using our algorithms, and let's hear to that. I hope you can hear the sound. So it was not 100% correct, but it was close. So we can say that we can say that the audio beat means the visual beat was very efficient to predict the audio beats from just from the video. So if we now in our future work, if we try to integrate both of them, I think the performance will be much better than the only audio, the only video, and using the leader selection, it will be much better. So for conclusion, we have the Kuramoto's oscillator, and we can improve the equation more to filter more error, suppress more noise, and increase the accuracy using this kind of mathematical phase oscillator models. And then this model can really adapt to changes in the tempo, which is a very key factor which the beat tracking algorithm lacks behind. And then creating an simulation environment for this kind of experiment to happen will be a real challenge, and we are trying to work on that as well. And again, the latency and the noise are nightmares for us. So every algorithm which we work on must have ensure that they have the least latency, and they can suppress or erase out the noise from the signals. And measuring the quality of synchronization is, or the synchrony, is a key factor, because if you heard about the butterfly effect, like the butterfly which flaps a wing in South America, can cause a tornado in North America. So it's like you had a small error like 0.001, and if you keep multiplying that, the error keeps on increasing, and that can affect a lot in during synchronization. So this kind of challenge is really worthy of looking into and studying. So hopefully one day synchronization will be achieved with humans and robots, and they will have a better relationship. And these are the paper for reference which we were published and we talked about. So hopefully I will take any questions if you have any questions. So thank you for listening.